Hi cheme friends, Akshay here, and up until now whatever simulation program that we have done was through an assumption that we will be taking steady state, right, when time tends to infinity. But what happens in cases where, say, your plant is just about to run, or you are testing a new equipment? In that case, we need to study its behavior through dynamic simulation. So what is a dynamic simulation? So dynamic simulation is a use of computer program to study how the system behaves as time changes. So through one run, we'll specify a period of time, say from time 0 to time 10 seconds, and we will be able to understand what's the dynamics of the system under the given conditions. So for this purpose, we will be taking a look at an example of a double pipe heat exchanger, because for illustrative purpose of dynamic simulation, I think it's a fairly easy example, and you can check the description box where we have shared it in the form of a PDF. You can take a look at it, and let's begin. So you can pause the video and take a look at the question, think about it for a couple of seconds, and we'll start it. So you can pause now. Alright, so we have been given a double pipe heat exchanger, right? And we have been given that we need to heat cold water at 25 degrees Celsius. We've been given the dimensions of the heat exchanger and the mass flow rate of the cold water, and we've also been given that we need to use hot water to heat up this cool water, and the mass flow rate of the hot water has also been given. And let the cold side fluid be at the tube side while the hot fluid is in the shell side. Okay, that's quite evident from the figure given here. So using MATLAB, we need to simulate the system such that spatial and temporal variations in the temperature are visualized. Okay, this sounds a little complicated, but what this sentence actually means is that we need to find how the temperature changes with respect to space, which is the dimension. So we've been given length equals 80 meter. So we'll be just taking a look at how the temperature changes with respect to the length of the heat exchanger as it flows through the heat exchanger, and the temporal variations means that how this temperature will change with respect to time. So this might be an animation is what it will be later on. You'll see what it is. And we've been given two cases, so we have to see counter current and co-current cases and look at how the temperature changes with respect to time and the dimension of the heat exchanger. And we've been given the constants. Since it's water on both shell side and tube side, we'll be using specific heat capacity, density, as well as the overall heat transfer capacity, which has also been given. We can assume a few things, that no change in physical properties obviously, and at time t equals 0 before the fluid enters the shell and tube. Okay, so we'll just assume that prior to this liquids being put into the double pipe heat exchanger, the temperature is at 25 degrees Celsius. So if we remember that case number one is the counter current configuration, and we'll take a look at that right now. And here we have the figure of the double pipe heat exchanger, and we'll be taking a look at case number one. So step number one will be to divide the length of the heat exchanger into several nodes. So when length ranges from 0 to L, which is L equals 80 meters in our case in the problem, if you remember, and L will correspond to N, and between 1 and N there will be obviously nodes, and these nodes will be equidistant with a length of delta x between each of them. All right, and if you're familiar with finite difference method, it's similar to that. All right, so we have hot fluid entering here, and cold fluid entering from node number n. So hot fluid from node number 1 and cold fluid from node number n. So since the mass of the two tubes don't directly interact with each other, just the mass, so it doesn't make sense to do mass balance, since whatever mass is entering each of the shell or tube side, the same amount of mass is exiting. So what we have left is energy balance, since energy is interacting with each other within the system. So heat energy will be transferred from outside to the inside, and hence we'll be taking a look at that. Look at this figure here. So let's look at this element here. So this will be I, which we will use for generalization, and this will be I minus 1, and this will be I plus 1, right? So accumulation term, which is over here, will be equal to mCp into, where m is the mass in this area. So we have rho 1, which is the density, into area of cross section into the length of the node. We'll get the volume when we multiply area into the length of the node, right? And we multiply it into density. We have the mass of the contents of the given node, and we have the rate of change in temperature with respect to time. Then we'll take a look at the terms which correspond to the energy related to the flow. So since it's a counter current heat exchanger and we are looking at the energy balance of the inner pipe, we have mcp m1 cp1 into t1. And one thing to remember is that rho and cp are the density and the specific heat capacity are the same in our case, since both of them are water. So I might as well have written it just rho and cp, but okay, just in order to understand the difference between the two, I just specified that. All right, so we have m1 cp1 into the temperature at node ti plus 1. So we have the flow which enters from node ti plus 1, it enters into node number I, right? So we have m, and so this term is there. So this is energy in, and obviously, as I just explained, this will be energy out. So why isn't it I minus 1? We'll know that when we are writing the code. It will be quite obvious later on. And of course, this is the heat exchange which takes place. So this is U A delta T. So the delta T is between the outside pipe which supplies heat into the inner pipe minus the temperature at node I within the pipe. So there will be some heat interaction taking place between the heat exchanger outer tube and inner tube, and hence this term. And finally we get a differential equation where we have the rearrangement from the previous terms, and finally we get this equation, and this is just the energy balance for the inner pipe. All right. Moving on to the energy balance of the outer pipe, we have again the accumulation term. However, in this case, the area will be the area of the annulus. So it will be the area of this cylinder, rather, right, the area of this cylinder minus the area of the inner cylinder. So it will be pi r square r square 2 minus pi r square 1. So this will be the area of the annulus into, again, the volume. And I hope you'll understand this term, which is the energy is due to flow, as already explained in the previous energy balance of the inner pipe. And if you remember, this term would be the energy due to the heat exchange, which is positive in the previous case. As you can see here, it's positive here because energy is flowing into the inner pipe. However, it's negative here because the same amount of energy, in order to balance the energy, we have to subtract from the energy in the outer pipe, right? So again we get a new differential equation where we have dT2, which is T2 is the temperature of the outer pipe, whereas T1 is the temperature of the inner pipe, obviously, and we get a system of differential equations, which is this and this, for case number one. So we are done with case number one. We won't be delving too deep into case two, because since we've already understood how the energy balance of the system works, for case number one, which is counter current, it's pretty self-explanatory when you take a look at the co-current system. So we have energy balance. Again, we take this element of the inner pipe, and we have the accumulation term, and the difference in energy is due to flow, and the difference in energy is due to heat transfer, giving this final differential equation. And similarly, when we do the energy balance for the outer pipe in case 2, we'll have this equation. Now, if you have any doubts as to why we got this equation, you can refer to the previous section, or you can pause the video and take a look at each one of these terms one by one, and I'm sure you'll understand this pretty easy.
Although we will be doing both the cases, as in the co-current as well as the counter current case in this video, we will look at counter current case in a slightly more deeper manner. Yes, I will show you both the codes, but we'll use counter current to analyze, and I think it will be fairly simple for you to look at how the co-current will work, since we have already developed the model equation in the previous section. So let's take a look at the MATLAB environment, and let's begin now.
Okay, so we are in the MATLAB environment, and we'll be taking a look at case 1, which is the counter current heat exchanger configuration. So we will first take a look at what these are. So this is basically the inputs which are already given in the question. So L is the length of the pipe, R1 is the inner radius, R2 is the outer pipe radius rather. Wait. And we have uh, set number of nodes as 10. Okay, we'll analyze how nodes affect our output later on. And we have mass flow rate, which is equal to 20 kg per second for the cold fluid, and specific heat capacity and density already given. We have mass flow rate of the hot fluid, and we have specific heat capacity and density, which is, both of these are equal actually if you see, because it's already given in the question, because that we can ignore the changes in temperature. Now the interesting thing comes here. So we have AC1. If you remember, in the accumulation term, we have in the tube side heat exchanger on the left hand side. You can go back and take a look at it again in the video, and you will see that we have AC1, which is the cross sectional area of the inner tube. This is done in order to find the mass within the area of interest, which is node number I. And we have a cross sectional area of the outer tube, which is the annulus, because we are subtracting this R1 square because we want to find the total volume of the outer cylinder, which is the total volume of the outer cylinder minus the volume of the inner cylinder, which gives us an annulus shape, right? And we have the inlet temperature of fluid 1, and we have inlet temperature of fluid 2, all given in the question. And we had to assume that the initial temperature of the system is at room temperature, which is 298 Kelvin, and the overall heat transfer coefficient, I think, was 400 in the question. And how do we find the number of the total length of each node? So that will be done by dividing L by N. So we have 10 nodes, so total size of each node will be equal to 8 meters, because that's how it works, right? Because it's 80, L equals 80 divided by N, which is 10 in our case. And we need to find how many seconds we want to observe this dynamics of the heat exchanger, and dt is the time steps between which we want to run the simulation. I hope you're understanding until now. If you're not, and if you want to take a look at the code, you can just email us at cheme.friends@gmail.com. It's in the description box below, and we will send you the code, no problem. We are actually considering to start a GitHub account and just put everything there for you guys to just take it and take a look at it. Anyways, now we have x, which is line space between 0 and L. So we want to see the spatial variations as well. So what we did here was specifying things for to find the temporal variation, but we need to find the spatial variations as well, right? Between 0 and L, we want to find how the temperature is changing within the tube. So this term is just done to later on we'll see how it works, right? Like it's just here. And we need to create an array which consists of the initial conditions for T1, which is the temperature of the inner tube, and T2, which is the initial condition of for the temperatures in the outer tube. And we will be initializing the derivatives, the time derivatives of both the cases. We are also creating an array for t as t, where t ranges from 0 to time final with step change of dt. So we have already specified that the step change is 1 and time final is equal to 1000. So we will be observing this system and how the temperature changes with respect to time as well as length of the double pipe heat exchanger. So this is why we have made it. Now we'll come to this loop. It looks very complicated, but it's not. Okay, trust me. uh, okay, we'll go through it one by one. So we have created an index j which ranges from 1 to length of time. So we have we know the length of this, which is equal to 1001, so it will range from 1 to 1001, right? So through each loop we will see that the time changes, and so will the temperatures, because we are updating the derivatives. Okay, so we'll see that now, right? So we have CLF. This is for clearing out the data of the figure that comes out from the previous loop. So we are doing that. And okay, we'll see how what difference this makes if you don't know what it is about. Okay, so we'll come to the energy balance of fluid 1. So I'll take you back to the equation for case number 1. So you can see the rate of change in temperature with respect to time for fluid 1 is given here. And coming back to the code, you might see that the temperature. Okay, so we don't have any boundary conditions as such for node number 1 to node number n minus 1, right? We have a boundary condition for node number n. So for 1 to n minus 1, we will just write the generalized code. Okay, we'll just write the generalized equation. And for node number n, we will put in T1n, which is equal to 298 Kelvin. As you might remember, it is the boundary condition for our inlet of the cold side, the rather the tube side fluid of the double pipe heat exchanger. So in this case we'll have T1n, and yeah, so this will give the derivative of temperature with respect to time for fluid 1. And similarly, for the hot side fluid, we will write a generalized equation for node number 2 to n, whereas we have a boundary condition node number for node number 1, right? So we have the boundary condition T2n, which is equal to 363 Kelvin, and this is what will be substituted here. So the inlet and the outlet of the tube side and the shell side fluid will remain constant as such, but it will change as it enters into the double pipe heat exchanger. I think I'm explaining it in a basic way, not meant to, you know, test your not meant to test your intuition or whatever, but I think you have strong imagination. Okay, here we have just used the Euler rule. So you can see that we are updating the temperatures, and we have the derivative here with respect, and we are multiplying it into time if you remember the Euler rule. And we will plot x, which is the array consisting of length from 0 to l depending on, and the difference between 0 to l depends on the size of each node, which is given. Wait, where is it? Yeah, it's given here. So it'll depend on how many nodes we are using. So one thing you might have thought of, it's quite intuitive if you ask me. More the number of nodes, more accurate your code will be, right? And we will plot it. We have axis size for the x-axis 0 to 80, which is the length of our heat exchanger, and the y-axis ranging from 290 to 400, because thermodynamically it cannot be less than 290 or greater than 400. So we are writing x label, y label, holding on for the for plot between x and T2. So we will see how both of these temperatures are changing with respect to time. And we are writing pause because the iterations will run really fast. So we want it to stay there a bit, and it'll look like an animation when we are done with it. All right, so let's go for run, and let's see what happens. So you can see here how the temperature changes with respect to this is the red is the hot side fluid and the blue is cold side fluid. So this thing will run for I think 100 seconds, because we have paused it for 0.1 seconds, and we have put time final equals 1000 seconds. So I think it'll run for around 100 seconds. We don't have so much time, so just have to press Control C because it won't stop as it is. And you can see the point at which we where we stop the code is this. One thing I just wanted to show you is what CLF, what happens when we remove CLF. So yeah, you can see how this goes, right? So it's recording the previous iteration as well. Quite messy for us, looks cool, but okay. Let's stop this by pressing Control C and close. And yeah, let's take a look at the co-current flow. It'll be very quick. Since we have already seen how counter current system works, I think it's pretty obvious how the co-current system will work. So you can pause the video and take a look at this and check if you believe this is supposed to be the correct answer. And let's just run the code. We'll understand. Let's just make time steps a bit larger here, because as you remember it took too much time. So let's make the time step 10 seconds. So yeah, let's see how it goes. Yeah, so this is for co-current, and you can see it'll get over in 10 seconds because the pause was for 0.1 seconds. And yeah, that's it. So yeah.
I find it so satisfying to look at the dynamic simulation, and it's really fun to watch them. So, thanks for watching, and consider subscribing to the channel. We just started an Instagram page recently where we'll be sharing chemical engineering facts and memes. So do check it out, and it's really encouraging if you subscribe to the channel if you are new here. So take care, and thank you. Bye.